Hallelujah. Okay, so we are in good shape. The screen recorder is now working again. For those of you who are watching this video, there's going to be a second video that's like 6 minutes long. That'll be the first kind of portion of this, so you may need to kind of go back a little bit to watch that. So, cool. Okay, hooray! I am now not as distracted as I was. So, let's go ahead and look at the next ones. All right, next one is Valerie. Alrighty. 7A. How are we going to set that up? Okay, we can work with this. I'm sorry, 7B. Okay. Did you just change that on me? You might have. That's cool. That's cool. I'm glad I noticed this because I was like, I closed it like I swear it said 7A before. So 7B. Okay, how many moles of each element are present in a 100-gram sample of ethanol? Okay, so this is, which homework was this? The mole concept, I guess? Oh, we're doing 7B. Cool. Okay, so with this is how many moles of carbon, hydrogen, and oxygen are in 100 grams of ethanol? Well, to answer this, we probably want the answer to part A, so I guess we are going to do that anyway. So, for part A for this one, it asks us how many moles of ethanol are in that 100-gram sample. Ethanol happens to have this formula, which could be written, I know, as you've seen, CH3CH2OH, but if you just combine all those elements, I typically refer to it this way. If we do the molar mass of this, it should be what, 46.0, I don't know, 5, 6 maybe grams per mole, something like that. Well, it's close enough. We'll be okay. So if we want to do part A, we're taking 100 grams of ethanol. And if we want to convert it to moles, we just have our molar mass on the bottom. And we'll get our answer, which is what, 2.11, I think, if I remember last time I did this, 46. 2.17, we'll say. I guess we need another sig figs. Okay. Whatever I get out of this. You might have a slightly different answer. It's fine. Your exam is multiple choice anyway, so like you're not going to be super far off. Okay. If we do that, we saw that's how many moles we had of ethanol. So that was part A. In order to do part B, it's a little bit easier if we already have done part A. Once we know how many moles of ethanol we have, it's a little bit easier to say, okay, well, let's rewrite this question. Instead of saying 100 grams of ethanol, let's say we have now 2.174 moles of ethanol. And then it simply becomes a matter of looking at how many of each atom we have in ethanol in general. So if we have this, I can't write it apparently, C2H6O, that tells us that we have 2 carbons per ethanol, right? That's what the formula tells us. Remember that we can then extrapolate this to say, oh, well, we can have 2 dozen carbons per dozen ethanols, or 2 moles of carbon for every 1 mole ethanol. Right? We can take each element separately if we were really interested, and we can see that each mole of ethanol will have 6 moles of hydrogen atoms in it, ethanol, and then 1 mole of oxygen for 1 mole of ethanol. We can get this information from a chemical formula. Right? If you were to break this molecule apart, if you had 3 of these molecules, you broke them apart, you would end up with 6 carbons at the end, right? Because you had 3 of them, you broke all of them individually, each one had 2, so as a result you have 6 total. If you have 6.022 times 10 to the 23rd ethanols, you have twice as many carbons because each ethanol had 2. And so these are the conversion factors we get out. And so if we want to see the moles of each element in this, it simply becomes a matter of going from moles of ethanol to your moles of your carbon or hydrogen or oxygen. And if we set it up for carbon, 2.174 moles of ethanol. We're going to put 1 mole ethanol on the bottom, and we're going to put 2 moles carbon on top. And as a result, we get 4.348 moles carbon. Again, this might be slightly different because I rounded my molar mass, but it should be somewhat like that, right? So that's how you would set that up. And then the rest would be the same thing. You just have a different conversion factor. For oxygen, it is 2.174, and for hydrogen, it would be 6 times. So you'd have 12 times, 12 point whatever at the end there. Okay? Yeah, so it's easier because the way that these kind of things are designed is that you'll use kind of questions you just answered to help you move forward. So, okay? Awesome. All right. Okay, that was those two. Let me see here if there were other questions. Let me scroll up a bit. Nope, that was it. Okay, so I'm happy to take more. We have, excuse me, about to sneeze. Excuse me. But I can go till maybe 12:15 or so if you really want, because I know we started a little bit later with the technical snafus. So I'm happy to just keep answering questions if you want to write them, if you want to ask them verbally. All right, Valerie's getting another one. Sounds good. And so, yeah, just let me know. Whatever you want me to go over, I'm happy to. All right. While you're typing that, by the way, a lot of the 101 students, apparently have never taken a Canvas quiz before, somehow. And so what I did was I just put a fake one so they can see the format of it. I'll do that for you guys too. I'll import that into your class. Yes, it is recorded. Alright, so we're doing number 10. Okay. So similar question. Yeah, similar, slightly different, but not, but it will be similar. So, let me see here. Need to make this visible. Okay, and then, import, okay, let me answer your question first, and then I'll put up the fake one. Keep losing it on the units. That's chemistry. You've summed up the entirety of Gen Chem in one sentence. So, totally. Okay, so how many carbon atoms? In 0.5 grams of glycine. What we'll want to do first is probably find the molar mass of glycine, which, again, I know it's a more written out molecule, but we had condensed it earlier, right? We had H5NC2O2. Normally you don't write a formula like this. You do carbons, hydrogens first, then nitrogens, then oxygens, but that's okay. We don't have to worry about it. If we're doing the molar mass, this one I do not know off the top of my head, so we would have to do 5 hydrogens plus... You've got it already?
Yeah.
Cool. Well, good. I'm still going to write this out, and then you can just tell me the number so I don't have to actually calculate it. Okay. Okay, so that's how we would do it. For anyone who's watching this later, maybe forgot how to do molar mass for some reason, somehow. Okay, what's the number we get?
Oh, I got 75.068.
Cool, sounds good. It seems reasonable, so Cool. So that's our molar mass for this thing. So if we're going from carbon atoms and glycine, now that we're starting with grams, remember that if we want to kind of work with anything in chemistry, we probably are going to need to convert something to moles. So if nothing else, convert something to moles, right? You can always go from grams to moles once you know the molar mass. Right, and so now we're trying to see how the heck do we go from moles of glycine to atoms of carbon. And if we kind of look back here, we saw, oh, that's right, we can go from moles of our compound to moles of the element using the formula, right? So maybe it makes sense for us to go to moles of carbon next, in between those two. And we know, so as written, we're going to need 3 conversion factors, 1 for each arrow here. Grams of glycine to moles of glycine is already right here, that's our molar mass. Moles of glycine to moles of carbon, you can kind of set that up here. We know that for every glycine molecule, we have 2 carbon atoms. So for every mole of glycine molecules, we have 2 moles of carbon atoms. And then the last one, from moles to atoms, that's just Avogadro's number. So our third one would just be 1 mole of carbon equals 6.022 times 10 to the 23rd atoms of carbon. And so that might just be the last bit there. So we're going now from moles to atoms. So setting it up, what do we have? 0.5 grams. I'm going to say gly. We have grams is going to go underneath. All glycine. We have now our second conversion factor was moles of glycine to moles of carbon. Moles of glycine needs to go on the bottom so it cancels out. Moles of carbon goes on the bottom so it cancels out now, and then we have atoms of carbon on the top. And so that would be the setup, and then you just calculate it from there. And whatever you get would be your answer. So let's see, probably it'll be something times like maybe 10 to the 21, 10 to the 22, somewhere around there, probably. And yeah. Alright, so hopefully that makes it a little bit clearer. And yeah, I totally get it. Sometimes it's worse when it's moles to molecules, because it's like they look so similar, right? Molecule has mole in it. 4 of the letters of molecule are mole. So yes. If it were like molecules of water, you'd still use Avogadro's number for that. So atoms and molecules, you'd still use Avogadro's. No, it's not weird to say that. It's certainly common. Students have all sorts of difficulty with this, so it's totally not unusual. So in terms of like getting the units right, though, does that mean kind of like setting up this plan idea, or just kind of like if you'd like to explain more, maybe I can offer some hints as to what might help. And as she's writing that, I mean, if anyone else has other questions, you know, where I'm here, so happy to answer them. All right. Oh, and then Yana, this is being recorded, just so you know. Yeah, no problem. Yeah, I totally get that. The Roomba has known. Oh, the worst is when it like yanks out the router from the wall. It's like, why is the internet down? It's because the Roomba freaking attacked it. It's like, come on. Okay, I see. Yeah, I get that. So, it's just really understanding this relationship. I think this is the part that you're having trouble with. Page 175, number 10. Hmm, is that from like the moles and reactions worksheet? Is one of those page 175? Okay, cool. Then I'll pull it up in a sec. Okay, but to go back to this, yeah, this is kind of the it's a little bit unusual because this thing is it's not very useful practically. I mean, why do we care how many carbon atoms are in this many moles of ethanol? We don't. There's not a purpose to it. So that I think is why a lot of people have trouble with it, is because it's not very practical to ask these things. These are all just kind of ways of kind of describing these things, but again, it's that's probably the reason it's not making very much sense to you, is because there's not a reason to do this. And so, I apologize for that, but it's important that we understand kind of how chemical formulas work in the context of reactions, so that when we're balancing things, we understand these relationships between atoms and molecules, and then moles and all that. So, yeah, it is confusing. Yes, I get it. And it's worse when you're going from moles to atoms, and it's like they really mean the same thing, but we have two different units to describe it that are really different from each other. And so I get it. I definitely sympathize with that. So I remember in like AP Chem when they started moles, I was like, what the hell is this? Like, why are we even? Drove me crazy. But yeah. Don't worry though, after this, we don't really talk about individual atoms again. So you can throw it out of your brain after the exam. We talk about moles all the time, but not individual atoms. So if that's any consolation. Alrighty, let me go ahead and pull up this thing real quick. Let me also steal that practice quiz so I can get that going, so you guys can see the format. Okay, so that's importing. Good. So let me pull up the assignment. There it is. Okay, so it's downloading real quick. We're looking at page 175. Okay, I found it. So nitrogen and ammonia and all that fun stuff. Okay, let's do it. So this will be on our like reactions, I guess, or stoichiometry maybe. Page 175, number 10. What's up? Were you gonna say something? No, got back to hiding. Okay. So we're doing nitrogen combines with hydrogen to form ammonia. That's something we've definitely seen. I'm going to go ahead and balance this because we've done this, like, we've already used this equation so many times in class. We've already balanced it so many times, but that would be the first step of this problem, is you'd need to balance, write the equation and then balance it. So the question is asking how many grams of ammonia are formed when 145 grams are consumed of nitrogen. All right, and so this one is, I guess, what we did yesterday. We're going to kind of follow the same idea here. We're going to start with our grams of nitrogen, because that's the number we do know. Since we don't have information about hydrogen, we don't have to do it twice. Remember, if it did say we also had 200 grams of hydrogen, we would have to do both, right? But since it's just one reactant given, we just work with that number. We know we're going to end up needing to go to moles of nitrogen. From moles of nitrogen to moles of ammonia. This process is exactly identical for all of these. We just changed their compounds that we're using. Later on, we'll start tweaking this, but for right now, we only have grams to moles, moles to grams. That's it. So, a little bit easier for us, because we can just replicate the pattern. as we go through. We don't even have to think about it. So, as always, we'll need one conversion factor per arrow here in our plan. Numbers 1 and 3 are molar masses, because that's how we're going between moles and grams. So number 1 is the molar mass of nitrogen, which is 28.02 grams per mole. Or I could even write that as a conversion factor. For ammonia, for number 3, which is another molar mass, that one is 17.034 grams, is 1 mole ammonia. I have that memorized because they use ammonia so much as an example, but again, you may need to calculate it. And then the other one is just our mole coefficients. So number 2, and these is always the ratios. So we have 1 mole of nitrogen is equal to 2 moles of ammonia. And those are just the coefficients from the reaction. So we have the 1 and the 2 are those numbers. Hi, little dude. I have like 6 dogs surrounding me right now. One just keeps coming on and just keep adding. It's pretty funny. Okay, so now that we've got that, we can go ahead and do this. So we're going to start with 145 grams of ammonia. We'll set this up. So we're going to go ahead. I'm sorry, we had nitrogen, not ammonia. So we're going to put our grams of ammonia on the nitrogen on the bottom, mole on top. We'll have our ratios. We're going to put nitrogen on the bottom, so it cancels out. And he begins the reverse sneezing, as always. Poor Oz. And then we would just have our molar mass at the end there, and then whatever number you get out would be your answer. You get grams of ammonia, and just remember, round that to 3 sig figs, because that's what you started with. So I don't want to calculate it. You can calculate it, but shouldn't be too bad. Okay. Alrighty. Yeah. Oh, I don't think she's talking to us. Okay. Okay. Gunna, are you talking to us, or is that just background? I can't tell if you're like trying and it's just like really faint, or if it's just background. So we'll see. Okay. We have one. Okay, sorry. So yeah, I can hear you. Yeah, totally.
Oh, really?
Yep.
Oh, I'm so sorry. I didn't know you could hear me. My mom is on.
No, it's not as funny. I was like, I can't quite hear it, but I hear someone talking. So no, that's not a problem. That's not a problem.
Sorry.
No, don't be sorry. Okay, so we've got blah blah blah. Nickel reacts with this stuff. Oh, that's fun. Okay, complex problem here. More complex problem. Yeah, we can take a look at this. Okay, dokie. No, stop trying to do that. Okay. Alrighty, let's see. So, nickel can react with gaseous carbon monoxide. This is number 1 on, I think, one of the exercises. So, nickel reacts with gaseous carbon monoxide to form nickel, or tetracarbonyl nickel is what we would call that. That's something you'll learn to name in Chem 2. Cool. So we can just throw a reaction here. Nickel plus carbon monoxide turns into this kind of what's called a complex. Hopefully the balancing is not too bad on this. Just got to stick a 4 here, and then that's done. Okay, we have other metals that aren't going to react. We have 94.2 grams of a mix of metals. And we are going to end up with 98.2 98.4 grams of this complex here. What is the mass percent of nickel in the original kind of mixture of metals? So, this is, I like this one. It's a bit tougher, makes you think a little bit more. But we have two numbers here. So with kind of word problems like these, they can totally throw you off, right? Because there's often a lot of information and you have to try and figure out, okay, what goes with what and how do I make sense of all this stuff, right? That's the skill that is necessary for this. So we have two numbers in this. We have 94.2 grams of this mixture of metals, and we have 98.4 grams of this nickel compound. And so, with the kind of stuff we've learned so far, having this number of the mix of metals is not going to be really useful for us in the context of a reaction, right? Like, if we put 94.2 grams of this mixture of metals, we have no idea how much of that is nickel, right? We don't know that. We can't figure that out from this number. That's what the question is asking us. So, we're going to ignore that number. This 98.4, though, we can do something with. If we want to find the mass percent of nickel, that just means that would be the same thing as saying what's the mass of the nickel over the mass of the mixture times 100%, right? That would be what we're doing. So we already have the mass of the mixture, 94.2. We do not have the mass of the nickel. So we are going to try and figure out how to find that. And so with that, we say, well, how about this other number? What can I do with that? Is there a way I can get nickel out of this? And that's where we're going to use our reaction skills. We know, okay, we made this amount of nickel tetracarbonyl nickel. And we can figure out how much nickel it actually took to make all that. So we can say, okay, we're going to go from the grams of this nickel business to moles of it, to moles of nickel, to grams of nickel. And so we can set this up just like before. 98.4 grams of this guy. I'm going to have to do some calculation here. Let me look up nickel's atomic mass real quick. We're looking at 58.69 plus 4 times 12.01 plus 16. Okay, the molar mass I got was 170. Does that sound about right? 170.73 grams of this. Then we can go to our reaction and say, the coefficients are just 1 and 1. And then we just need the mass of nickel, which would be the atomic mass, which I just had, 58.69 grams over 1 mole nickel. And then we will end up with some grams of nickel whenever we do this. I'll let you worry about the calculation part of this. And then once you get that number, then you can plug it in here. Whatever mass you get here, then you'll plug in and you can get your mass percent. So that'll be whatever number you get here over 94.2 grams for that mixture. Times 100%, whatever it is. So whatever number you get, plug it in there, and you'll end up with your mass percent. Okay? Awesome. Alrighty. Other questions? In the meantime, I have to figure out how to upload this to YouTube. The other one from my phone. Other questions? Anything at all? Alright, I have apparently just uploaded this to YouTube on my phone. That's pretty cool. Okay, so the first half of this will be there. Okay, here we go. We have the eyeballs. Oh no, it's the same question again from Valerie. No, just kidding. What would we like to do with this? We are distinguishing between molecules and atoms this time. It may be a good idea to do all of this, actually. Let's do it. This will be something number 4. We have 1 mole of hydrogen. How many molecules do we have? How many atoms? And what's the mass? Yeah, David. So, earlier, my screen recorder was not behaving itself, and it kept causing me to have to restart my computer, so I had recorded like the first 10 minutes on my phone. And so the rest of it, it's going to just come in 2 videos. That's the point. So you'll have a super short video to start and then a longer one. Yeah, cool. Alrighty. Cool. And then what's the mass? Okay. So, moles to molecules. Fun one here. So, it may be good for us to distinguish between molecules and atoms in the context like this. Molecules are atoms that are bound together. So, kind of, yes. So, that would be for B. It would be Avogadro's number times 2, for sure. For part A, it's just Avogadro's number. And for part B, it's times 2. And that's it. That's how we would do it. An easy one, perhaps. We should get Avogadro's number for the first one, right? Because a molecule is where you have multiple atoms put together. An atom is an individual atom. So, very circular definition there, but suffice to say, molecules are compounds. Atoms are individual elements, right? So, this molecule, a mole can be molecules or atoms or whatever. It doesn't matter. So, for how many molecules are 1 mole of hydrogen, H2, that is Avogadro's number of molecules. If we look at atoms, it would be 2 times this number. Because we have 2 atoms per molecule. So if we have 6 molecules, we have 12 atoms. And so it would just be twice as big as that, whatever that number happens to be, 12.044, I guess. And then the mass would just be the molar mass, so that would be 2.016 grams. So it's just the molar mass, because we're given 1 mole to start with. So that's going to make all of our calculations super easy. So this is just the same thing. Yeah, so think atoms are generally going to be a bigger number than molecules will be. So, because molecules are a bigger thing, right? Molecules have multiple atoms in them. So your number of molecules is generally going to be smaller or equal to your number of atoms. It just depends. Like with the glycine, we had 1 nitrogen, so 1 mole of glycine would have 1 mole of nitrogen. But it had 6 hydrogens or something, so it would have 6 times Avogadro's number of atoms of hydrogen per mole of glycine. So, yeah, you just would do 2 times Avogadro's number, and that's it. Yep, that's it. So, thankfully, because it's just 1 mole. If we really wanted to formalize this, we would say, okay, well, we've got 1 mole times 6.022 molecules for 1 mole. And so 1 times 6 is 6, right? We don't really need to do the 1.2 or 1.00. So I guess with sig figs, oh, shame on me. Boom, boom. Oh no. Oh no, this one also. There we go. We'll fix our sig figs, won't we? So. Because we're given 1.00 moles, we'll be good and apply our sig figs. We are given some sig figs in our original number. So. Alrighty. Anything else we'd like to go over? I guess for David, I can just tell what we've gone over so far. We did some balancing. We did some stoichiometry business somewhere. We had some looking at the number of atoms per mole of things. A lot of counting the atoms. Here we did some stoichiometry, so some kind of math with chemical reactions. And then we did a little bit more complex example of that. And then more of this Avogadro stuff. So that is what we have done so far. That one's the same question from before, Valerie. So I think you didn't copy the new one or something, so, or uploaded a different one. Yeah, so. Let's see here. Ethanol is the molecular formula. What's the mass of 1 mole? What's the average mass of 1 molecule? Okay, got it. So this is again, So the mass of 1 mole of ethanol that would be, we'd already calculated our molar mass earlier. So therefore the mass of 1 mole would be 46.06 grams. What it means by average mass, since we're looking at 1 molecule, that's where isotopes actually make a difference, because you know, if we're looking at one, we would need to know, are these all carbon 12s, are these all hydrogen 1s, or all these oxygen 16? You know, we would need to know the isotope. So that's why it's asking average. So we're going to just avoid the problem of dealing with individual isotopes by just saying what's the average. So the average mass of 1 molecule, this is the mass of 1 mole of ethanol. With 1 molecule, we're looking at just 1 unit. What's the number under the H? That's a 6, sorry. I think I had written something else and I just tried to cover it up, so cool. So for 1 molecule, though, we know that 6.022 times 10 to the 23rd molecules would weigh 46.06 grams. That's another definition of molar mass, right? These all equal 1 mole, right? These are all equal to each other. 1 mole of ethanol. Oh my gosh. Now I'm writing C6. Okay. C2H6O. 1 mole of ethanol is equal to 46.06 grams of ethanol, which is equal to 6.022 times 10 to the 23rd power molecules of ethanol. So all of these three are equal to each other. And so if we want to say we have, what's the mass of one molecule? Let's start with one molecule. We would need to put molecule on the bottom. And we're going to put our mass, the molar mass, on top. And so we're going to get our number here. So something tiny, 46.06 divided by 6.022 E23. And we get 7.649 times 10 to the negative 23rd power grams. So something really tiny, right? So we're looking at one molecule. The first question, we're looking at 6.022 times 10 to the 23rd molecules, which is 1 mole. The second part, we're looking at one molecule. So a tiny, 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 tiny amount. And so that's why it doesn't weigh very much. And since it weighs so little, having those differences in isotopes would make a big difference in our number. So that's why it says average, so we don't worry about that. So because if we take 6 times 10 to the 23rd, on average, they will all weigh that number each. Just on average. Awesome. Awesome, awesome. Alrighty. We got time for like 1 or 2 more, if there are a few extras. I'll also be posting these like kind of lecture notes. I'll post the like what I've written out here, so if you want that, it'll be up there too. Oh, sorry, Michaela. I know you really wanted to talk too, so that's unfortunate. I mean, is it more like you just don't remember how to unmute yourself, or is it like actually not working? And then also, are you using your phone or computer? Oh, your laptop, okay. So it's then in the bottom left of it. Oh, it worked on your phone. So the chances are it's probably the settings.
I don't know that.
Alexa's listening in. Uh-oh. It's probably in your settings then. If you go to the, like, near that mute button on your laptop, on that bottom left, there's a little cog wheel for user settings. If you click that, it worked. Okay, cool. There you go. It worked.
I just so it's got all the settings messed up.
Got it.
So I was just wondering, like, conceptually, when you have this this molecular formula for ethanol, how, when you add up all the masses and you get this mass, how do you know it's Avogadro's number of that?
So that is how we originally defined the moles, or molar mass. So molar mass is actually defined as the mass of that number, Avogadro's number, of whatever you're looking at. So it works out for us that we can look on the periodic table and add up the average atomic mass of all the elements involved, and we'll get out the number that will make this work. So conceptually, these, as you can see, one molecule or one atom weighs a tiny amount, something we would never be able to make an instrument to be able to weigh. So, I can't speak to the calculations that Avogadro did to figure this number out. Something to do with gases and gas laws, because that's kind of the science he was doing at the time. This number just happens to be what he was able to calculate in terms of how many molecules are necessary for this. So it's a totally complex, I guess, proof of something. So I don't know the origin of it. So unfortunately, I could maybe look it up. It's probably interesting. But suffice it to say, for our purposes, it is a definition. For us, molar mass is the mass in grams of 1 mole of a substance. And 1 mole for us is defined as being 6.022 times 10 to the 23rd molecules, or atoms, or whatever you're looking at. Since we're looking at a compound, we're talking about molecules. If we're looking at an atom, we're talking about atoms. Just one element, we're looking at atoms then. So, it's just a definition for us. So 1 mole is equal to 6.022 times 10 to the 23rd whatevers, and that is also equal to your molar mass. And so the only thing the only thing that changes is the middle number there. So whatever substance we're looking at, the right and left will always be the same. So if we're looking at water molecules, or whatever it is, let's see. For water, we calculated earlier. It's 18.02 grams water is equal to 1 mole water, which is equal to that many molecules of water. If we have glucose, or I don't know, calcium, what did we do? What was the one that had 100? Calcium chloride, about 111 grams, or 110.98 grams. So this kind of equality holds true for anything. Any element, any compound. The only thing you change is the molar mass. And so the rest of the relationships still stay the same. Okay? Hopefully that makes it a little bit easier to get your brain around.
Oh, kind of.
Kind of.
No, not really.
Not really, okay.
I'm going to look up a video about it. I need to be able to conceptualize it, and I'm not going to be able to remember the...
Got it. Yep, I totally get that. And so, yes, this is a tough thing to think, because we can't really visualize this many molecules, right? It doesn't make sense. This is, again, a harder thing to visualize, and again, it's not something we ever really talk about. We don't talk about individual molecules because we can't really measure them. So I totally get that it's a little bit harder to wrap your brain around the concept of this idea of this number of molecules, for sure. I could probably look one up for you as well, so. But we can figure that later. Yeah.
I think it might be, like, my confusion is something about density, and I might need to just look up something about mass in general.
Got it. So, yeah. Mass, for us, you can think of it as weight. So same as weight. So if you go and weigh out, whatever, a pound of flour, that would be 453.6 grams. Don't need to know that number, by the way. But, it's essentially just how much of something you have. Density is similar. Density we also think about in terms of weight, right? You think about, this bag of feathers is not very heavy because it's not very dense. I get that. The density is a relationship between the mass and how much space it occupies. And so there's a lot of connection between the two topics, and we're used to it in everyday speech saying, oh, this is so dense, oh, this is so heavy. Technically, those are two different things, but for us in real life, they're the same, right? We could say, oh my gosh, this thing is so dense, this brick is really heavy, this brick is really dense. Same thing. That's definitely a point where things can get a little bit confusing. So, and that's a terminology thing. So density is all about volume. It incorporates how much space something occupies. Mass is just how much of it is there. And I get those two are also kind of conceptual. So if it helps, I can try and find a more conceptual definition of molar mass. I don't know if it will be any different, but I can take a look at a couple videos. We'll see. So, but yeah, it may be just just taking some time to think about it. So.
Thank you.
Alrighty, maybe time for one more question. And just so we all know, I am putting like a practice. Actually, I can switch the screen over to it real quick so you can see. Okay, so if I go to student view, okay, let me hop over to. Can I explain empirical formula again? Oh my, okay. I don't know that we'll have time for that, but let me show this real quick, and then I will kind of do a very quick empirical formula. You may just want to watch the video again, Gianna, but yeah, we'll see what we can do. Okay, so let me just show this so you guys can be prepared for what it's going to look like for your exam. So, oh, hold on, I've got to leave student view for a sec. Let me put, oh, I didn't put it here. Okay, that's why. Well, it didn't. There it is. Okay. So I've got a practice quiz for us. So this is what y'all will see when you go onto Canvas, our homepage. Got a little fake practice quiz here worth no points. How this will work is it's just going to show you the format of how an exam will look. So in this case, we have 2 questions in 10 minutes. When you are ready, you will click Take the Quiz. Couple things to this thing. Oh yeah, I mean this is just a fake little thing just to show you. So your timer will be in the side here, as well as like a little hop bar. So if you need to hop between questions, say you're on question 25 and you're like, oh wait, I need to go back to question 2, you can very quickly like hop between them. Not very useful right now because I've only got 2 questions. They're multiple choice, so you'll be able to choose your answer. And I'm going to go ahead and choose this one. And so you'll answer them all. You can mark your question, say, I'm going to come back to this one later. And then that's also going to mark it up here on the side so that you'll know, okay, I flagged this question to go back later. And then you can click that. When you're done, you'll click Submit. And you will not get your feedback right away because I'm scheduling it to give feedback the next day. So it will just give you a score. It's not going to tell you what you got right or wrong, or even what you put. So just that's all I can do in terms of like preventing cheating. So that's all I can do. So yeah. So and then there we go. So it's not worth any points because it's just for practice, so you can get familiar with how it's going to look. Okay, so that's that. I'll link it for you right here. Okay, let me see. Go to my channel, videos. This one. Okay, so I'm just going to link that right here. So it is 1 for 101, but it's the same idea. So there you have it. So we'll just take a look at that one. There's like 10 problems in that one. So if you get it on the first one, that's great. So, all right. Cool. Okay, so I'm going to close that. I'm going to stop